In this video, we're going to analyze a parallel RLC circuit operating in it, or with a step response, the step response of a parallel RLC circuit. So in this case, we've got a current source that prior to t equals 0 is shorted out of the circuit with the switch being closed here. You'll note that that also then shorts out all of the three other devices in the circuit. So the initial conditions, V0 and I0, are 0. Our first step, once again, is to transform this into the frequency domain, where the current source transfers in as IDC, some constant I, that turns on at t equals 0. So we've got IDC over S to represent the fact that it wasn't a constant, but that this DC current is being applied at t equals 0. This is the transform of, or the Laplace way of representing I of t, U of t. Now the capacitor comes in with an impedance of 1 over SC. Once again, there's no initial voltage on the capacitor, so there's no current or voltage source associated with this. Similarly, the inductor comes in as S over L. Once again, there's no initial current in it, so there's no voltage or current source here, and the resistor just comes as the resistance. To get started, let's write a KVL in terms of the voltage across this parallel connection that we're representing as V of S. So the current going through the capacitor, again we're writing a KCL. The current through the capacitor is just V of S, but we're going to drop the of S's here, divided by the impedance 1 over SC, plus the current through the inductor is V over SL, plus the current through the resistor is V over R. The sum of those three things then equals IDC divided by S. Now let's factor, again, what we want to do is we want to solve for, in this case we'll solve for V. Once we know the voltage across this, we can determine the current through any one of those branches by simply taking the voltage and dividing by the impedance. So let's get started here by factoring out the V, and when we do that, we're left with 1 over SC. That just brings us an SC in the numerator, plus 1 over S times L plus 1 over R is equal to IDC divided by S. Now dividing both sides of the equation by this term right here to solve for V, we have then V, and again it's V of S, is equal to IDC. We'll go ahead and bring this S term down into the denominator, the S coming from the fact that it was a unit step function applying at t equals 0, or triggering at t equals 0. Then we've got SC plus 1 over SL plus 1 over R. Alrighty, once again we want to get this polynomial here in terms of descending powers of S, with the highest power of S with a coefficient of 1 in front of it. So we see that we've got an S here, we've got an S in the denominator that we need to get rid of, and we'd like to get rid of this C. So if we multiply numerator and denominator, well, let's see, first of all, let's go ahead and distribute the S. We get an S squared term here, the S's cancel here, and we get an S over R. So V then, coming up here, V is equal to IDC divided by S squared times C plus 1 over RS plus 1 over L. Now, let's go ahead and get the coefficient associated with this S squared term to be 1 by multiplying numerator and denominator by 1 over C. And when we do that, we get the expression for V of S is equal to IDC divided by C over S squared plus 1 over RCS plus 1 over LC. You'll notice that this right here is the quadratic term that we ended up with when we solved this circuit using traditional differential equation techniques. And we took this and set it equal to 0, and that became our characteristic equation. So just realize that the same math shows or pops up in many of our approaches to solving the same kind of circuit. Now, let's go ahead and assign some values for the current source and the capacitor, the resistor, and the inductor. And also, just for grins, let's instead of just solving for V, let's solve for I as a function of S. That's going to equal V of S divided by SL. So when I said I, really what I'm saying is let's solve for the current flowing through this inductor by taking the voltage across here and dividing it by the impedance S times L. When we do that, we get in the numerator, we still have IDC divided by C, but when we're dividing both sides by L, let's go ahead and bring the L up into the denominator of the numerator and keep all of our constants together. And then we've got this S term, which will be multiplied by S squared plus 1 over RCS plus 1 over LC. Now, let's let IDC equal 24 milliamps, or 0.024 amps. We'll let L be 25 millihenries. L equals 0.025 Henry. C will let equal 25 nanofarad, 25 times 10 to the minus 9th farads. And R is going to be 625. So taking those values, plugging it into here, we get then, and let's be explicit, let's call this I sub L. I sub L of S then is equal to, multiplying everything out, we get 384 times 10 to the 5th in the numerator. 384 times 10 to the 5th in the numerator, and in the denominator we have S times S squared plus 1 over RC turns out to be 64,000. 64,000 S, and 1 over LC turns out to be 1.6 times 10 to the minus 9th. So plus 1.6 times 10 to the positive 9. We're now ready to transform this back into the time domain by doing a partial fraction expansion on the roots of this denominator, and then using the Laplace tables go back into the time domain. So in order to do that, we need to find out what the roots of this are, or we need to factor this. And when we do so, we find that S is equal to negative 32,000 plus or minus J 24,000. So just plugging this quadratic term into the quadratic formula, we get those two values for S. And the two factors then associated with this are S plus 32,000 minus J 24,000 and S plus 32,000 plus J 24,000. I've gone ahead and written this now on this next slide in the factored form. So I sub L of S in its factored form is this, which is now ready to be expanded into its partial fractions, where we have associated with a factor S a K1 over S. Then the term associated with this, we call that the positive term. We have K2 over S squared plus 32,000 minus J 24,000 plus K2 conjugate over S plus 32 plus J 24,000. Now we'll start to evaluate these constants, first of all working with a constant over the S to the first power term. We have then, we're going to multiply both sides of this equation by 1 over S. So I sub L of S times S, and then evaluate it at S equals 0. And when we do that, on the left-hand side, we have then 384 times 10 to the 5th. Now, multiplying by S cancels the S here, and then evaluating what's left at S equals 0, we have then 32 32,000 minus j 24,000 times 32,000 plus j 24,000 is equal to, now over here when we multiply this side of the equation by s, we end up with an s term here. There's nothing down here to cancel. We multiply by an s term here. There's nothing to cancel it. So when we evaluate this side at s equals 0, those two terms go away. Now this term, when it's multiplied by s, the s's cancel, and we're left simply with k1. We've done enough examples of this that hopefully you remember how to do this. We end up with that being equal to k1, which, when we evaluate that, we get k1 is equal to 0.024. To find k2, we're going to multiply both sides of the equation by this factor. Multiply both sides by, so multiply by s plus 32,000 minus j 24,000, and then evaluate what is left at s equals the root associated with this factor, or negative 32,000 plus j 24,000. When we do that, we get then, and we'll multiply both sides of the equation by that term. This term here, of course, cancels, or when it's multiplied by this term here, the denominators cancel and we're left with k2 all by itself. When we do it to this term and this term, they don't cancel, and so when we evaluate that factor at the root, with a value of s that makes that factor go to 0, both this term and that term drop out, and we're left with just k2 on the right-hand side. And on the left-hand side, we have then 384 times 10 to the 5th. In the denominator, we have evaluating this at s equals negative 32,000 plus j 24,000. We have an s term here, so that's just negative 32,000 plus j 24,000. Of course, this term canceled when we multiplied both sides of the equation by that, so we're still left with this term evaluated at s equals negative 32,000 plus j 24, or negative 32,000 plus j 24,000. That's the s, plus then those two terms still there, plus 32,000 plus j 24,000. Of course, the negative 32,000 and the positive 32,000 add to 0, and when, of course, and we have over here on the right-hand side, as we already pointed out, is k2. When you evaluate this, you get that k2 is equal to 0.02 angle 126.87 degrees. I've gone ahead and written in then the completed partial fraction expansion for I sub L of s. And we note then that we have this term here, 0.024 over s. Well, that just transforms back into the time domain as 0.024 u of t. And then we have these other two terms, which are conjugates of each other, and from the Laplace tables, we know that when we have two terms of this form, in the time domain, it goes back to 2 times the magnitude of k, e to the minus alpha t cosine of beta t plus theta u of t, where, in this case, alpha is this constant right there, 32,000. Beta is the value in front of the imaginary part, is the coefficient of the imaginary term. In this case, beta is 24,000. And theta is the theta associated with the constant over the positive root, or the factor associated with the positive root. In this case, theta then is equal to a positive 126.87. Now, we take these values and plug them into this, and we get these two terms coming back into the time domain as 2 times the magnitude of k, so 2 times 0.02, the magnitude of k is 0.02, e to the minus alpha, but alpha is 32,000 times t, cosine of beta t. Beta is the 24,000, so cosine of 24,000 t plus theta, and theta is 126.87 degrees. And this whole thing here then also is multiplied by u of t to show that it kicks on at as a step response as the switch closes at t equals 0. 2 times 0.02 is 0.04. And we now have our I of t is equal to 0.024 u of t plus this cosine term with a phase term. Now let's compare our results for I of t here with what we would have gotten using the classical differential equations solution approach for an underdamped circuit. We recall that I of t would have been of the form e to the minus alpha t times b1 cosine of omega sub dt plus b2 sine of omega sub dt. In other words, the classical approach gave us what is known as an in-phase and a quadrature term, or the quadrature idea is that the sine of an angle is 90 degrees out of phase, lagging the cosine of that angle. So the sine term lags the cosine term by 90 degrees. It's sometimes referred to as the quadrature, the in-phase and quadrature terms. And then, of course, we have the final current associated with it. Now, for this case, it would have then given us e to the minus 32,000 t times b1, which, again, we're just pulling this solution from our previous experience, minus 0.024 cosine of 24,000 t minus 0.032 sine of 24,000 t plus the final current in the inductor, which would be 0.024. Now, to satisfy our curiosity, we need to show that this form of I of t, again derived using classical differential equation techniques, which gave us a cosine term and a sine term, we need to show that this is equivalent to this. And to do that, let's use phasors to combine these two terms into a single term. Well, this is going to be, this term right here would be negative 0.024 angle 0. And this term here would be minus 0.032. Now the sine we change to the cosine. Cosine of, let's see here, cosine of, no, not cosine, it would be minus 0.032 angle negative 90. There we go, converting the sine to the cosine term and then writing it in its polar form. The cosine of the angle minus 90 degrees is equal to the sine. So adding those two terms together using phasors gives us 0.04 angle positive 126.87. So we then have I of t is equal to e to the minus 32,000 t times the cosine of 24,000 t plus 126.87 degrees, and of course we've got the let's move this over here. We've got the 0.04 multiplying all this. So the 0.04 is the magnitude of the combination of those two things. So 0.04 times that plus 0.024. And what we see then is that this and this are exactly equivalent to each other. Amplitude of 0.04 times e to the minus 32,000 t cosine of 24,000 t plus 126.87 degrees times u of t for the oscillating term, and then the final term is the 0.024 u of t. And so we get a nice feeling inside when the Laplace technique yields the same result we got using traditional differential equations techniques to solve or to analyze these circuits.